first thank the organizers to give me this opportunity to talk about my work that I am doing on jets for last few years. And this particular work is a method which we developed with Mr. Mukhopadhyay and Ritesh Singh when I was at IISER Kolkata. So that is the name is dynamic radius jet clustering algorithm. So that I'll be talking about today. Okay. Okay, so the date is wrong anyway. So let me first motivate you that as we already know that the high energy colliders are actually very, very crucial in advancing our knowledge of particle physics that we are seeing for decades, more than a decade now. And one of the central object is basically jet, which usually appears from high energetic quark or gluon, which are basically colored particle. So those are so the jets are a central object in any high energy collider. Okay. So now, as in the morning session, Songshoptak already pointed out that so not only quark and gluons can produce jet, it is like boosted heavy particles can also produce jets if their energy is very, very high, and then those jets are slightly different from characteristics are slightly different from the QCD jets, and they are called fat jets. And now, so nowadays any BSM or SM studies actually focuses on these objects, jets and fat jets, and try to extract some things from it. And now I will describe this thing. So current days algorithm that we use are basically KT, anti-KT and CR algorithm, which are called fixed radius sequential recombination algorithm, jet algorithm that we use. They are good algorithms, but they have some deficiencies like inadequate that we wanted to go further and solve. Okay. So that method is like variable radius, which is slightly different from the fixed radius algorithm that we implemented, and I am trying to motivate you and show you that that is useful. Okay. So let me give you very, very brief and quick introduction to jet. Jet is basically collection of bunches collimated hadrons. For example, let's say if a quark or gluon, which is a colored particle, is energetic enough, then it tends to shower, and after the shower they hadronize, and then those hadrons are extremely collimated, and those hadrons are detected at the detector, but they are very, very collimated, and those collimated hadrons, the collection of those collimated hadrons we usually capture and call jet. Okay. So that is the appearance of the QCD jet, we say. They tend to be light and narrower in size. But then again in the high energy colliders, which is for example at the LHC or any future colliders, what happens that heavy particle can also be produced at a very high boost. Okay. So for example, W boson, Z boson, or top or Higgs boson. For example, Songshoptak talked about W boson, which can produce a fat jet if that produced W boson is actually very, very boosted. Okay. So that has been shown here. Let's say for example, top quark actually decays. It has three body decays. Let's say bottom and W subsequently decays to two quarks, a quark and anti-quark pair. And in a sufficiently boosted region, it can actually decays. These three decay products come within a very small cone, and the showering from these quarks again produce a jet. But the characteristically, this jet, for example, W jet and W jet, Z jet, or top quark jet versus this quark and gluon jets are slightly different, because this tend to be narrower in size, and mass tends to be very small, whereas top quark and these are slightly fatter in size, and their masses are heavy. But in any case, we have to cluster these highly collimated bunches of hadrons from the detector, and we need to get the jets. And for that, what we use are called jet clustering algorithm, or sometimes we call jet algorithms. So be it a narrow jet or a QCD jet, so we need an algorithm, and that algorithm is called jet clustering algorithm. Okay, so for example, this is one. This is the, let's say, it is an iterative method basically. So you put the list of whole 4 momenta from an event, 4 momenta of the hadrons that you detected, and you put it in the list, and you go through this procedure, and you will get the jets. But we have to define basically 2 distance parameters, and based on that distance parameters, we have to optimize and iterate over the things. And so popularly, there are like 3 different algorithms that we use: are Cambridge-Arkin, KT, and anti-KT algorithm. And importantly, from this, what I want to show, there is a parameter to this theory apart from an integer parameter that is there as p. This R naught parameter, which typically sets the radius of the jet. Okay, so this is this particular method, we call it fixed radius algorithm, where the typical size of the jet is fixed by the radius R naught. Okay. So now, as I mentioned that in the QCD case, this is tend to be smaller the size, whereas in the fat jet case it tends to be bigger in size. But if we give only one parameter, then we will not be effectively capturing the 2 different sizes in a single go. Okay. So that's where we actually propose that if we can modify this R naught to kind of a dynamic quantity by modifying it to R naught plus sigma I, where sigma I is defined as the basically standard deviation of delta R, the distances of the constituents of a jet when the jet is getting formed. Okay. So if we do that, we can show that it can be useful. So in our case, so earlier it was like CA, Cambridge-Arkin, KT, and anti-KT algorithm. So in our case, we call it dynamic radius jet algorithm, and that's why we like for the same thing, same p values, we just give name drCA, drKT, and drAK. So those will be for future reference. So now our question was like, why this? So now one might ask why this particular variable is useful. So there are 2 reasons that we found useful, that why this is useful. One is like this sigma I is basically the standard deviation of the delta R's between the constituents of a jet, and that is basically the fuzziness of a jet. And since the fat jets, the jets coming from the heavier objects, tend to be fuzzier, so that's why this works. That was one of the explanation. Other explanation is that there are substructure observables which are useful in discriminating from normal QCD jet, from the top jet and W jet. So if you see this energy correlation function, which is defined the same way as we defined earlier in this sigma I definition, slightly different from it, and you see that this tends to be higher for the top jet, tends to be a little lower for the W jet, and for the QCD jet it tends to be smaller. So this is actually from an observation from the atlas. So this already tells that if we use that parameter, it could be useful in dynamicizing the radius of the object. Okay. Having said that, let me show some of the examples where we could see potential use of our method or of our development. So this has been implemented as a plugin to already existing framework by which we cluster the jet. It's fast jet, the 3rd version of it, and the implementation is available in GitHub. And then we potentially used it in 2 different types of events. One is in a proton-proton collision at 13 TeV. In the top, and the final state is top and jet. Why did we choose this top and jet? Top will give us fat jet, and whereas J, which is basically quark or gluon, will give us narrow or QCD jet. So whether we wanted to see that whether we can get 2 different size objects from a single event. And another example which is not within the standard model, where we incorporated some sequential model where bottom partner has been called, and then this bottom partners actually decays to heavy bottom partners decays to top and W boson, and where we can see the utility of our model. And this has been implemented in model building, and then event generation has been done in MATLAB and Pythia. Those are. And let me illustrate one particular event. So basically, the event here is in the eta and phi plane, when these dots are the hadrons, and the sizes of the dot represents the energy or PT of the those hadrons. Okay. So now from the simulation, what we can see that these three big dot collections are basically three prongs of the top quark, and this is the quark or the gluon. Okay. And now both represent the same event, exactly the same event, but one is clustered with standard antiquity with 0.5 radius, whereas the right side has been clustered with the dynamic radius with antiquity, and the starting radius R naught is 0.5. Now what we can see is that this particular jet, which is QCD jet, which tends to be smaller, that has been captured by antiquity algorithm, standard antiquity algorithm, and also our algorithm correctly. Whereas this particular these three prongs could not be captured by the antiquity algorithm. It has been captured as two different jets, whereas our algorithm could capture the whole decays of the top quark. Okay. So that's the thing that we could achieve with this algorithm. So this is for a particular event, and maybe for the best event that we could see within our sample. Now, but we wanted to see that whether this is gaining at least statistically something. So for that we defined. So before that, let me tell that this is a jet mass distribution. Okay, for two different cases. So the shaded ones are for the standard antiquity, and the lines ones are for our algorithm. And here what we can see that for the QCD jet, so this is the green, these are represented by the green. So the mass for both the cases are actually similar, the distributions are similar. And another thing that we achieve is that this acceptance. How do we define this? This number of top we could reconstruct with a particular algorithm divided by total number of events that we produced. Okay. So for standard antiquity algorithm with 0.5 radius, we see that we could capture only 14% of the events that we generated, whereas with our algorithm we could actually capture roughly 49% or 50% events. So that is a big improvement that we can show. And on the right side, what we plot is the final radius that we get with our dynamic radius algorithm. So here also we can see that starting from 0.5, the QCD jet, which is represented by the green curve, here its final radius is not large enough. It can grow and the max up to 0.6 or something, whereas for the top quark it could grow up to 0.75 or 8. Okay. So that's the achievement we get, and then we tried to see that what would be the this acceptance variable that we defined with respect to let us say the radius if we choose. Okay. So this is for dynamic radius for that is our method, and for the antiquity we can see that almost everywhere we get higher acceptance for our algorithm, whereas for the antiquity it's lower. Okay. So now so this increases and then it sharply drops. This drop is not because that it is performing poorly. It is performing poorly because it is now started to capturing a lot more things which are essentially garbage. So there should be some optimal choice for this, and that we can see. Okay. So these three are for three different algorithm: anti-KT, Cambridge, and the KT algorithm. Okay. So this is for first illustration and then the illustration from a different theory where we have 2 tops and 2 Ws. Here also we can see on the left it is for anti-KT with 0.5 radius, and the top would not be captured here the whole thing, whereas in this on the right side we can see that we could capture both the tops very effectively with this algorithm, and again we can see that we get 4-fold or like 3.5-fold gain in the acceptance. Okay. So that is the thing, and then let me come to the summary that variable radius jet algorithms are actually useful in certain cases in search for BSM or SM, and we actually developed an algorithm which is called dynamic radius jet clustering algorithm, and we discussed the idea, implementation and utility of it, and it has application in the case of like heavy object studies and other things. And in the outlook, what we are now doing are like we are seeing the potential use of this application and trying to figure out how this can be useful in quark-gluon discrimination case or some event topology case, or finding the dark jets. And then the some of the studies that we are doing with CMS or Atlas Open Data to try to see its like sensitivity towards the pile-up effect and jet energy calibrations and other things. So that we are doing. And thank you everyone for listening.
Very important question. Is there any scale dependence in R naught? I mean, because clearly as a function of root S, I would assume the jet sizes will change, right?
It typically does, but we have some standard choices for the anti-KT, right? So, for example, if you want to capture the QCD jet in the anti-KT, we take it to be like 0.4.
No, that I understand. But since you're doing this acceptance studies, right now you use the 13 TeV data, right? So if you use some other data, I mean, it might be that your
optimal choice can be different.
Can be different.
Can
Okay.
be different. Yes.
But right now your code actually can use arbitrary values, right? Or
Yes.
Okay.
You start with some radius. So R naught is the starting radius, initial radius, and then it adopts its sizes accordingly.
Okay.
As it.
Nice. Thank you.
How that's been going into on today, because it's all at some point you do with every nation symbol Google and not there. I'll be able to all day in the art. Good radiation.
No, R naught cannot actually, the way we implement it, it can always increase. It's not R naught increases, but it starts from some R naught and the radius adapts and it always increases. Okay. And how big, if you ask, then I would say it's not a, yes. Then what will happen? Then the pile up will start come in, and then your mass distribution, other things will get screwed. So for our case, we see that for this case it is 0.5 is good enough, and then if you go 0.6, 0.7 in some cases, but not beyond that, it will be difficult.